We're going to go over an example for how to maximize a motor's power. So the first thing we need to do is we have to know a little bit about our motor. So here's our motor right here. It's a VEX 269 motor, and so what I did is I went out to the internet and I searched for the motor and found the specifications on the motor. So if I look at the specifications for this motor, let's go ahead and write those down. So this is a VEX 269. Its free speed is equal to 100 RPMs, which means that if there is no load attached to the motor, it would spin at 100 RPMs. So that's the theoretical free speed. The stall torque is equal to 8.6 inch-pounds. 8.6 inch-pounds, and what that means is if more than 8.6 or more inch-pounds of torque are on the motor, it will not spin. The other thing that we need to note here is at the bottom is that motor specs are at 7.2 volts. So I'm going to put at 7.2 volts. And so we know that those numbers come from 7.2 volts. So the next thing that we're going to do, once I have these things written down, a VEX 269 motor, free speed 100 RPM, stall torque 8.6 inch-pounds at 7.2 volts. And so that's all the information we need. The next thing we're going to do is I'm going to go ahead and draw an axle coming out of this motor. So the purpose for our example here. And then next thing I'm going to do is to draw a lever arm coming off of the motor. So I'm just going to draw a straight line here. So a lever arm comes off the motor. What we're going to pretend like in our simulation here is that we are putting a force of half a pound, and we're trying to lift that half-pound force with our motor. And so we're going to do some calculations to maximize the motor's power to do that. All right? And so the first thing we're going to do is we're going to calculate stall torque distance. So we know that torque is equal to force times this distance. So that's our formula. Torque is equal to force times perpendicular distance. Okay? And we know a few things about our motor. We know that the stall torque of our motor from right up here is 8.6 inch-pounds, and so I can go ahead and put that into my equation here. It's going to be equal to our force. Our force in this case is we want to lift a half pound. And so what we're doing is we're figuring out the perpendicular distance, the distance that this lever can be from the motor and basically stall out. So all we have to do is divide, manipulate our formula. Perpendicular distance is equal to 17.2 inches. And so what we've done here is we figured out that if we put that that half-pound force 17.2 inches or further away, it's not going to lift the weight because the motor is going to be stalled. Too much torque is going to be put on the motor. All right. So that's our first distance. So we know that it has to be inside of 17.2 inches to be able to work. So let's figure out what the maximum power distance is. And so we're going to calculate the distance for the motor at maximum power. So what's the distance if our motor is at maximum power that we can gain the benefit of having the maximum power coming out of the motor? And so again, it's the same formula. Torque is equal to force times perpendicular distance. Our torque this time, we know that half of stall torque is maximum power because it's a linear equation. And so we've seen that represented in the presentation. And so we know that half of stall torque is maximum power for our motor. And so I'm going to put half of 8.6 in for that, which is 4.3 inch-pounds. That's equal to our force, which is half a pound. And now we're going to figure out the distance, the perpendicular distance for our motor to be at maximum power. And so if we do that, we get 8.6 inches. So if our motor is at 8.6 inches away, or excuse me, our force is at 8.6 inches away, that's going to be the maximum power we can get for our motor. All right? And so it's going to be working most efficiently, the most power put at the motor if we put this force 8.6 inches away. All right? The next thing that we're going to calculate is output torque. And so we're basically going to do this in a different way. And so if I write output torque here, we can go ahead and calculate that. The torque out is equal to, again, force times perpendicular distance. The output torque is what we're going to be calculating for. So our force is the same, half a pound. Our distance now has changed. And so what we are going to do now is, let's say that our distance is it's something we can't change in the equation, a variable we can't change. And so we're going to figure out what the best situation is. And so we're going to say that in this case, our distance is 5 inches. All right. So in this case up here, we could move the distance of the force. In this case, we have a constraint where that distance can't be moved. And so we're going to just calculate the output torque. So 0.5 times 5 inches gives us an output torque equal to 2.5 inch-pounds. All right. And so the last thing that we can do with that number, that 2.5 inch-pound number, is we can figure out a gear ratio that will help us get the maximum power out of this motor. And so up here, I'm going to go ahead and figure out what the gear ratio is going to be that we want to include in our system so that we can get the maximum power out of our motor at 5 inches. All right, so in this case, gear ratio, remember from our mechanisms unit, gear ratio is equal to torque out divided by torque in. Torque out in this case, what we want to get out of the system is 2.5 inch-pounds. So I'm going to go ahead and put that in. We want 2.5 inch-pounds. Torque in, what we're putting into the system, 8.6 is our stall torque. And so again, we want our motor at maximum power. And so we're going to divide that by 2. So this will be 4.3 inch-pounds. And so I take 2.5 and I divide it by 4.3. And I get a gear ratio of 0.58. We'll just call it 0.58. Okay? And so now what we have to do is figure out what gears we have available. So I'm going to call this choose VEX gears. So we don't have the option of just making a gear ratio perfect. We have to use some standardized parts in our system. And so if I go back and look at the VEX gears, the gear ratio of our VEX gears, the closest I can get to that 0.58 is a 36 tooth gear and a 60 tooth gear. So if I divide 36 by 60, I get a gear ratio of 0.6. All right, and so basically what we have said is that if we can figure out a way to include a 36 tooth gear and a 60 tooth gear on our system, and so if I go ahead and draw that here, I'm just going to put here is a 60 tooth gear, and here is here's my 60 tooth, here is a 36 tooth gear. If I were to use that gear ratio in our system, I would be able to lift this at 5 inches and it would use the maximum power of our motor. All right, and so there's an application of being able to use the information from the motor to figure out a gear ratio that will help you solve a problem.